this particular example. Any questions about why that's the answer? You do have a question or no? No, okay. So again, we saw the graph, did some math with it, figured out where on the graph it ends up breaking even, which means you got to do more than break even, so you have to sell more than 1,000 lamps. All right, now down here, listen up. On a graph, think about just the graph, okay? How do complex roots differ from real roots? We saw this yesterday a little bit. We got some answers where we figured out real roots and then we figured out some complex roots with I and all that. How were those answers with I different than the answers that were just regular real numbers in terms of the graph? So if we look at example 3. We did this one yesterday. We had a real root. We had a real root at 2, and then we had 2 imaginary roots, one at -3 plus or minus the square root of 3, plus the square root of 3i over 2, and then the other one at -3 minus the square root of 3i over 2. How does that differ in terms of the zeros when we actually use the graph? Yeah, the complex roots don't show up on the graph. Only the real roots do. So the question here says, on a graph, specifically on a graph, how do complex roots differ from real roots? Well, you can see the real roots on the graph, and you cannot see the complex roots. So real roots are visible on the graph. Complex roots are not. That would be an explanation of visually on a graph what things end up looking like in terms of the roots. Real roots are visible on the graph, complex roots are not. All right. Any questions here before we continue? Not much left to go through, actually. I think we've got, yeah, two more examples, then we're done. Here we go. Example 5. This one says, what are the solutions? This is different than asking where the zeros are at. Because what we have here are 2 separate functions. If you look at the graph, we've got 2 separate functions on the same graph, and it shows right here the intersection point is at that point there. We don't know exactly what that is because it's, I mean, it looks like maybe it's -1, 3, but we're not exactly sure. So right here, we're trying to figure out the solutions to this equation. This is different than figuring out where a graph crosses the x-axis because each side of this equation, listen up, each side of this equation is its own function. So this is sort of like when you were figuring out systems of equations, you were figuring out where the equations intersected. This is basically a system of polynomials where you're figuring intersection points of the 2 polynomials. So it's going to be a very similar process. So here we go. What's that? So you could do that, yeah. Yeah. So the question was, could you graph those 2 separately on your calculator and then find the point of intersection? Yes, that works. We're going to do this algebraically first. And then we'll go from there. So what we need to do, listen up. What we can do with this is if we treat this like a single polynomial, we can solve for the zeros of it if we treat it like a single polynomial, which means set it equal to 0. So let's set this thing equal to 0. So we're going to subtract 3x cubed. We're going to subtract 8x squared. We're going to subtract 1 from both sides in order to set this whole thing equal to 0. So if we take 2x cubed and we subtract 3x cubed, that's going to be -1x cubed or -x cubed. 5x squared minus 8x squared is negative 3x squared. The minus 3x doesn't change because we're not bringing an x over. And then we're bringing over a minus 1, and we're setting the whole thing equal to 0. Now, the whole idea here is if we can factor this, we should factor this. So let's take a look here for a second. I like to have a positive lead coefficient. So is everybody okay if I multiply everything on both sides by -1, just to change everything from positive to negative and negative to positive? So that'll be x cubed plus 3x squared plus 3x plus 1 equals 0. Now, listen up. There's a lot of conversations happening. Let's go ahead and focus in, please. Thank you. So something I want to bring back to your attention before we continue this problem here is it was from, what lesson was that? 3.3, I think it was. Yeah. Section 3.3. So in section 3.3, we learned about the binomial theorem. And we did a lot of work on this last page with the binomial theorem. And so what I want to do is draw your attention real quick to Pascal's triangle here, specifically row 3, where it says 1, 3, 3, 1. And if you have a binomial that has been cubed, these are your generic coefficients of those things, 1, 3, 3, and 1. And if we look here, our coefficients are 1, 3, 3, and 1. So for this particular problem, if we see 1, 3, 3, and 1 here, that could be a clue as to how to factor this. And we also learned that with our variables and exponents, this first one has the exponent that's on the outside of the binomial. So that would be cubed. And then as we go through it, if there's one variable, then the exponents decrease all the way down until there's nothing. If there's two variables, then this first one decreases, and if there's a second one, the second one would increase in terms of its value, but there's only one variable here, which is the same pattern that we see here as well. So we've got the coefficients from Pascal's triangle of 1, 3, 3, and 1. So because these are being added together, and we see a plus 3x plus 1. We've got 3, 2, 1, 0 with our variables and exponents. This actually is x plus 1 cubed. Because it fits that binomial theorem. Now, I know that was sort of a coming out of nowhere situation, but we learned this last week. So that is something that can happen here. If you notice that, which is, again, it's not going to be an easy thing to notice because, you know, knowing about Pascal's triangle is not necessarily an easy thing to do. I just want to go back to the last problem real quick and point out this one does not fit with that in any way. So using the graph on this one was kind of what we had to do. But right here, we've got ourselves a binomial cube. Which ends up being, if we were to solve this, if we cube root both sides to get rid of the exponent here, cube root that side, cube root this side, that ends up giving us x plus 1 equals 0. which means that x equals -1. X is equal to -1, which gives us the x value, listen up, it gives us the x value of the intersection of the two original polynomials. It's the x-intercept of that single polynomial, but we started with two polynomials, and so the x-intercept is right here at -1. So that's one of our answers there. Now, there's a multiplicity of 3 as well, which isn't really relevant here because we're not talking about a single polynomial at the moment. But if we were being asked that, we could say that. Eyes up here. Let's keep going. We have to do one more thing, though. Because if we're looking for solutions, first of all, there's only one x solution, which means there's only one point of intersection, which is good. But we need the y value as well. We have the x value at -1. We need the y value. So there's a couple things we could do. We could plug in -1 for x here and solve, or we could use synthetic division to evaluate when x is equal to -1, which is what I would prefer to do. So let's use synthetic division to figure out the y value. Now, it looks to me like the y value is at 3. So let's see if that works. So we'll use synthetic division. We'll put a -1 here. We'll go ahead and use the combined polynomial that we just did. So 1, 3, 3, 1 will be the numbers here. 1, 3, 3, 1. And hopefully the remainder, well, we'll see what the remainder is. So we bring it down, we're going to get a 1. This will be -1. That'll be 2. This will be -2. 3, that'll be 1, -1. And so that's 0. So that actually just only works to show us the x-intercept of that polynomial, which is fine. So we proved that that solution works with x equals -1. But that's not the actual intersection point. So we don't need that. We're able to validate that, yes, this is the x-intercept. So what do you think we could do to figure out the y value? Think about that for a second. We used synthetic division with the combined ones, but it only told us that -1 is the x-intercept, which is true, of the combined polynomial. What do you think we could do with each of these to figure out the y value? What's that? Not quite. We could plug x in. Something else we could do though. Here, let me show you. The other thing that we could do is, let's say, I'll use blue for this one, I'll use red for this one. I'm going to go back to what Rakai suggested at the beginning of this problem, and that is, if you were to graph those both separately, we would end up with that graph. Which means if we evaluate for x equals -1 separately in each of those, we should get the y value of the intersection, which appears to be 3. So that means we've got two functions here. We have y equals 2x cubed plus 5x squared minus 3x. And we have y equals 3x cubed plus 8x squared plus 1. So even though synthetic division didn't give us the point of intersection with the combined polynomial here, if we use synthetic division on each of those two, we should get the same answer for both. And it should hopefully be right around 3. Okay, is that what you said? Nice. Okay, here we go. Synthetic division with the blue one, synthetic division with the red one. Hopefully the remainder is the same on each of them, because that would indicate that the x and the y values are the same, which is this point right here. So here we go. I'm just going to do blue for the first one. So we're going to use -1 for x, and we're going to have 2, 5, -3, and then 0. 2, 5, -3, 0. We need the 0 on the end because that's the constant term. There wasn't a constant term, so therefore the value is 0. So here we go. Bring down the 2. We get -2. We get 3. We get -3. That's going to be -6, and that will be 6, and which means the remainder is 6. So actually, it does tell us that the y scale is 2. So that actually works out just fine. Because if the y scale is 2, if we go up 3 grid lines, that means that the y value is 6, which is good. So let's check it for the other one. I'll do the other one in red. So we're going to get -1, and then we're going to have 3, 8. What number comes after 8 for synthetic division here? 0, and then 1. All right, bring down the 3. And there it is. So both of those separate functions, both of the separate polynomials, when evaluated for x equals -1, gives us a y value of 6. So the point of intersection, the solution is right here, -1, 6. That's the answer. -1, 6. All right. Let's try the next two. Try to work through them maybe a little bit quicker. Hopefully the factoring is not going to need Pascal's triangle, but if it does, we can reference it. All right. So with number 5, now that we know that we're going to evaluate these separately using synthetic division at the end, we won't make this mistake again, but I just wanted to show that to you just to show that that does not work when you evaluate for the combined polynomial. It just tells you that, yes, this is the x-intercept of the combined polynomial, but we need to figure out the intersection points of the separate polynomials. So with number 5, let's go ahead and combine these. Now, the nice thing that happens with our x cubes on number 5a is what? They cancel out. X cubed cancels with x cubed because if you subtract it, it's gone. If we subtract 5x squared from both sides, that's just going to be a negative 5x squared over here. If we add 2x, that'll be minus 5x. And then if we add 24, that'll be plus 30 and then equals 0. And this one should be a bit easier to factor. What do you notice about all 3 of those terms? Yeah, and I'm going to say -5 because I like my Lie coefficient with my quadratic or polynomial or whatever to be positive. So let's divide everything by -5. So pull out the -5. We're going to get x squared plus x minus 6 equals 0. What does x squared plus x minus 6 factor to? I think we factored that yesterday. Sure. Take a look. What does this factor to? Other way. -2 and +3. Yeah, 2 numbers that multiply to -6 and add to 1 would be 2 and -3. Or sorry, -2 and 3. So -5, x minus 2, x plus 3 equals 0. So this one has 2 values of x. What are our 2 values of x? 2 and -3. Which means there are how many points of intersection between the 2 different functions? There's 2. There's a point of intersection when x equals 2. There's a point of intersection when x equals -3. We have to figure out the y values for each of those. So I'm just going to go ahead and draw a line over here so we can separate these problems. And over here, I'm going to write these 2 functions separately. So we're going to get x cubed minus 7x plus 6. And we're going to have x cubed plus 5x squared minus 2x minus 24, because we need to evaluate both of those for x equals 2 and x equals -3. So we're going to have 4 synthetic divisions to do on this problem, which hopefully won't take very long. If we're getting pretty good at synthetic division, this should be a pretty quick process. So let's give it a try. Let's go with x equals 2 first. So when x equals 2, not x, 2, we're going to have 1, -7, and 6. Here we go. Bring down the 1. 1 times 2 is 2. Negative 7 plus 2 is negative 5. Negative 5 times 2 is negative 10. 6 plus negative 10 is negative 4. Let's evaluate the next one for x equals 2. So that's going to be 2. And then we're going to have 1. Actually, you know what? I messed up. I forgot a 0. Okay. So we need, I'll just rewrite it. It's fine. So 2, we're going to have 1, 0, negative 7, and then 6. All right. Try this again here. So 1, 2, 2, 4, negative 3, negative 6, and 0. So we have an intersection point apparently at 2, 0. Let's find out if this one also gives us a value of 0 when we evaluate using synthetic division. So we're going to have 1, 5, negative 2, negative 24. Okay, bring down the 1. That's 2, 7, 14, 12, 24, 0. All right. So one of the points of intersection is the point 2, 0. We got that one figured out. Now we need to evaluate the other one. I'm going to go off to the side here and just do it over here. So when x equals 2, y equals 0. So one of the points of intersection is the point 2, 0. I'm just going to write that down here, 2, 0. Just to kind of save that for the answer. And then the other one, we're going to need to use negative 3 for x. So here we go, negative 3. And I can't forget my 0 this time. So 1, 0, negative 7, 6. Bring down the 1. Negative 3, negative 3. That'll be 9, 2, negative 6 again, and 0. Interesting. So it looks like they're going to intersect on the x-axis twice at the zeros. Huh. I'm going to double check with the graph after this one because that's kind of an interesting thing. So let's see. Next one, negative 3, 1, 5, negative 2, negative 24. Let's see. We'll bring this on down. The hole punch is in the way. All right, so 1, negative 3 would be 2 there. That should be under the 5. Negative 3 times 2, that's negative 6. Negative 8, 24, and 0. Okay, so 2, 0, and negative 3, 0. Those should be the 2 points of intersection of those two functions. Just to verify this, I'm going to head back to the graphing calculator because you can always check on your graphing calculator to see if that's where the things actually intersect or not. So our two functions are x cubed minus 7x plus 6. The other one is x cubed plus 5x squared minus 2x minus 24. So those two should intersect at both 2 and 3, or sorry, negative 3 and 2. Yeah, right there at the zeros. Interesting. 2 points of intersection, both at zeros of each function. Each function has an additional 0, but those are not points of intersection. So that's what we got. So we were correct. It just so happens that the points of intersection are zeros of each function. All right, let's try the last one here. And then we'll move on to the very last example. Okay, part B. Let's see, if we add x cubed to both sides, that'll give us x to the 4th power plus x cubed plus 2x squared plus 2x equals 0. So if we combine both functions, that's what we get. All right, now looking at this one, I think we might be able to factor this by grouping. Pascal's triangle is not going to work on this one. But I think if we factor by grouping, we'll be all right. So if we go back to factor by grouping, that means we're looking at just the first 2 terms. What can we factor out of this? Out of those 2, what can be divided out? X cubed. All right, so that would be x cubed, and we'd be left with x plus 1 in those sets of parentheses there. What can we factor out of the second 2x, okay, so plus 2x here, and that'll leave us with x plus 1. Yeah, that works. Because both sets of parentheses are the same, and that equals 0, so that means we can factor by grouping. So that's going to be x cubed plus 2x in one set of parentheses, and then x plus 1 in the other set. Now, we can actually factor out one more thing here. X, yeah. We can factor out an x from that. So let's do that. Get this entire thing factored out. Factor out an x here. So that'll be x squared plus 2, and then x plus 1, and then equals 0. So, of the possible zeros, which ones are real? That'll be a real 0. Okay. Well, this one? No, why not? Yeah, because of the exponent. Because if you subtract 2 from both sides, that'd be x squared equals -2. That would be positive or negative root 2i, or positive or negative I root 2, which is imaginary. So we don't need to mess around with this one because it's not going to show up on the graph. This one will, and this one will. This one's what? That one's -1. What's this one? Yeah, x equals 0. So the two real zeros here are, I'm just going to write them up here, x equals 0 and x equals -1. Those are our real zeros of the combined polynomial. So we again have to test using synthetic division twice for each value of x. So I'm going to try to write smaller on this one, but thankfully these are, well, these aren't going to be that much smaller because we're going to have a lot of zeros to fill in for. So let's go with x to the 4th plus 2x squared first. So here's 0 for x. We're going to have 1, 0, 2, 0, 0. X to the 4th plus 0x cubed plus 2x squared plus 0x plus 0. 1, 0, 2, 0, 0. All right, here we go. Bring down the 1. Bring down the 1. 1 times 0 is 0. 0 plus 0 is 0. 0 times 0 is 0. 2 plus 0 is 2. 2 times 0 is 0. 0, 0, 0. A lot of zeros. So that means the origin should be a location of a point of intersection, the point 0, 0. Let's plug it into this next one right here using synthetic division. So we're going to have 0. And then let's see, -1, 0, -2, 0. That's -x cubed plus 0x squared minus 2x plus 0. Get our line, bring it down. -1 times 0 is 0. 0 plus 0 is 0. 0 times 0 is 0. -2 plus 0 is -2. 0 and 0. Okay. So one of our points of intersection is definitely the origin 0, 0. Now we have to do the same thing, but we're going to evaluate with -1 here instead of 0. Let's see what happens with that. So once again, we're going to have -1 now. 1, 0, 2, 0, 0. Bring down the 1. -1, -1. That's 1, 3. -3, -3, 3, 3. So the y value looks like it's going to be 3. Let's try it with the next one. -1, -1, 0, -2, 0. Is it 3 for both? Anybody get it? Yeah, nice. All right, let's bring it down. -1 times -1 is 1. 0 plus 1 is 1. 1 times -1 is -1. -2 plus -1 is -3. -3 times -1 is 3. 0 plus 3 is 3. So our 2 points of intersection are the origin 0, 0 and the point -1, 3. All right. You can always verify that on the graphing calculator as well. Okay. We're definitely building here. I would say, so first of all, the only thing that I think is more complicated about these ones is probably the factoring, honestly. Like, this isn't any more difficult. It's just more of the same. It's more work. It's not necessarily harder work, except for the factoring. Especially if you have to use Pascal's triangle. All right. Last one here. This one, why is this one different? What's that? Yeah, it's an inequality. So here we go. Shh, listen up. What we need to figure out on this one, it says, what are the solutions of x cubed minus 16x is less than 0? What it's asking you is, for what value or values of x are the y values underneath the x-axis? So where do we get negative y values for given x values? Now, if you look at the function, take a look at the function here. Where are the y values negative? Yes, well, partially. I mean, x is definitely less than 0 here, but it's also less than 0 here, but the y values are still positive. So let's go ahead and figure out our answers first, and then we'll go ahead and do the algebra after that. So it says the blue portions show where p of x is greater than 0. So I'm going to use blue here. Okay. So here's blue. We doing okay? Okay. All right. So we got blue here. That's where p of x is greater than 0. All the y values are above 0 on the y-axis. It says the red portions are where it's less than 0. So that would be down here and down here. All right. Okay. We're just finishing up the notes. All right. So take a look. The whole point of this problem is to figure out on this particular function where we already have a graph, we can see the graph here, for what values of x make the y values negative. So that's the question here. And I want you to write that down. That is the question we're asking, and I want you to write that down. Everybody write this down, please. If you're dealing with an inequality.
Go to testing, we're back to group 1. That's juniors with the last name to start with the letters A through C. Please go to the Career Center at this time. Juniors last names A through C.
Anybody not done A through C? Need to go down? No? Cool. All right. So what values of x make the y values negative? So here we go. The y values are negative here and here. The values of x that those are associated with, did you get it in assignment yesterday? No? All right, there you go. The x values that are associated with the red would be x is less than negative 4, yep. And x is in between 0 and 4. So those are going to be our answers. So let's go ahead and write those down real quick. So we're going to say x is less than negative 4. Okay, or x is in between 0 and 4. That's what we're looking at here on our graph. Everywhere the graph is underneath the x-axis happens at an x value less than negative 4 or an x value in between 0 and 4. Like visually, does that make sense on the graph? Everybody see that? So this is our answer. Now we have to figure out how we can actually solve that using some algebra. So now that we know our answer and that we hopefully understand what we're trying to figure out, let's go back and actually do this using some algebra because we won't have the graph to look at on those problems. So we need to understand what's happening in order to actually make these determinations. So first thing we're going to do is basically we're talking about what value is negative 4. What do we call that on this graph? What's the name for that point at negative 4? It is it's a what? Yeah, it's a x-intercept. Yeah, it's a 0, right? So is 0, so is 4. Right? Every point where the graph crosses the x-axis is a 0. So what we're going to do is we are going to figure out the equation version of this for 0, just like we've been doing. Figure out the zeros of the graph, and then try to figure out what's going on with it. All right, thank you. So let's rewrite this in as an equation first, and then we'll deal with the inequality aspect of it later. So let's say x cubed minus 16x equals 0. Because what we need to figure out is where does that graph cross the x-axis, because that will be our definition. Yes. Did you get the assignment yesterday? No, you were gone. So let's factor this, just like we did for the previous problem. We can divide out an x from both of those. So let's do that first, factor out an x. And then we're going to get x squared minus 16 equals 0. All right. Inside the parentheses here, how does this factor? X plus 4 times x minus 4. Yeah, this is a difference of squares. So we're going to get x plus 4, x minus 4 equals 0. So, yeah, so we've got zeros at 0, -4, and 4, which is exactly what we see here. Now, the issue that we end up with is they're not all negative, right? They're not all going to be less than. Because the 0 here, if we said x is less than 0, that doesn't mean that it's going to be underneath the x-axis. X is less than 4 does, x is less than -4 does, but x is less than 0 doesn't really mean that. So that's where we kind of have to figure out what we're doing with this. We have our zeros. And so the objective here, by the way, is to give ourselves a quick sketch of the function. Now, what we're going to do, we're going to make a sketch of these functions down below. And if we were to sketch this function here, we could, because we talked about that over the last couple of days. If we were to sketch this function, this is a cubic function. There is no multiplicity, which means it's always going to cross the x-axis, because multiplicity means it turns around at the x-axis when that exponent is even. But we don't have any multiplicity, so we don't have to worry about that. Every exponent with our x is an odd exponent, which means it's going to cross the x-axis every single time. So it's going to start off, we have a positive lead coefficient, which means it's going to go negative as x goes negative, which is what happens here. It's going to go positive when x goes positive to positive infinity right here, based on what we know about a cubic function or an odd function with a positive lead coefficient. So it's going to go from underneath the x-axis to cross it at -4, go above, come back down at 0, and then come back up above at +4. So that is going to be our process here. So we have zeros. Let's just write this down. Zeros at -4, 0, and 4. Because that's going to be really important for this process. We don't really care where those local maximums or minimums are. We just care where it crosses the x-axis. That's our big thing here. And so once you see what the sketch looks like, you can then make your determination on where those things are happening. So that's what we're going to have to do for these last two examples here. So let's give this one a try. So the first thing we're going to do is set it equal to 0. And actually, I'm going to factor out a 2x and set it equal to 0 at the same time, because we can divide out a 2x. So that'll be 2x, and then we're going to have x squared plus 6x plus 6 is equal to 0. So just change it to an equation at first. Knowing the whole time we're trying to figure out for what x values make the y values negative, because we're still looking at less than 0. So what two numbers would multiply to 6 and add to 6? What's that? Okay, so how could we go ahead and solve this? what should we use to solve for x here? What method always allows us to solve? Quadratic formula. There it is. So the quadratic formula is what we're going to have to use here. I'm just going to do this off to the side. So we're going to say x is equal to the opposite of b, -6, plus or minus square root of, let's see, b squared is 36, minus 4 times a is 1, times c is 24, so that'll just be minus 24, over 2 times a, which is 2. So I'm just going to try to speed up this quadratic formula process a little bit. 36 minus 24 is 12. So that's x equal to -6 plus or minus the square root of 12 over 2. The square root of 12 has a perfect square factor of 4. So that'd be square root of 4 times the square root of 3. The square root of 4 is 2. So this is going to be x is equal to -6 plus or minus 2 root 3 over 2. Every one of our integer values is divisible by 2. So this whole thing can be reduced by a factor of 2. So that's going to be x is equal to -3 plus or minus the square root of 3. So we have zeros at, first of all, 0, because 2x equals 0 means x equals 0. So we have zeros at 0. We've got one at -3 plus the square root of 3, and we have one at -3 minus the square root of 3. Those are 3 zeros. Now, this is a cubic function with a positive lead coefficient. So again, this is down on the left, up on the right. We have zeros, let's see, -3 plus the square root of 3. Well, we know we have one at 0. How about that? Let's just put the one in the middle, because we know that. -3 plus the square root of 3. The square root of 3 is definitely less than 2, which means that there's a negative here. If you have -3 and then you subtract a number that's less than 2, that puts you maybe about here. We don't know. We don't really care. What we care is some sort of accuracy in terms of where these things are at. So it's going to come up from the bottom here, like that. It will then go above the x-axis from here to here. It's then going to drop down below between here and here. And then it'll go back above after here. So our answers to this one, this will be the last one we do. We've got this one right here is this point right here, because that's the smallest value we have. So we're going to say x is less than -3 minus the square root of 3. We also have, we're going to say, or x is in between this number here and 0. So -3 plus the square root of 3 is less than x is less than 0. Those will be our answers for those two there. If you want to use the decimal versions of those numbers too, you are more than welcome to do that, just to know where they are on the number line. That's fine with me. All right. We're going to go ahead and stop there. Who needs an assignment? I know some